These are the answers to homework 4J. Here are the definitions I would like you to know, and let's go to the questions. Number 1, combustion of a hydrocarbon yields 6.78 grams of carbon dioxide and 2.78 grams of water. If the molar mass of the compound is 85 plus or minus 5 grams per mole, determine its empirical and molecular formulas. When you're given raw data for a compound, in this case it's its combustion information, you can calculate its empirical formula from that. When you combust an unknown hydrocarbon, the oxygen combines with carbon to form CO2, and the oxygen combines with hydrogen to form H2O. If we've measured the masses of these two products, they will allow us to calculate the mass of carbon and the mass of hydrogen from the original unknown compound. The 6.78 grams of CO2 we can use to calculate how much carbon is in the CO2, because 1 mole of CO2 has a mass of 44 grams per mole, and out of that 44 grams, 12 grams of it comes from the 1 mole of carbon that's in it. So if I multiply by that fraction, 12.01 out of 44.01, that's going to tell us how many grams of carbon came from the CO2, and all the carbon in the CO2 came from the original hydrocarbon. So 1.85 grams of carbon in the CO2 exactly equals the 1.85 grams of carbon in our original unknown compound. 2.78 grams of water can be used to determine the amount of hydrogen in water, because 1 mole of water weighs 18 grams per mole, and out of that 18 grams per mole, 2 grams per mole of it is hydrogen. If we multiply by the fraction 2.02 out of 18.02, that'll tell us how much hydrogen is in the water sample that was produced, 0.3116 grams. And because all the hydrogen came from our original unknown hydrocarbon, that's how much hydrogen must be in the original unknown compound. So we've been able to calculate the mass of carbon and the mass of hydrogen in the unknown. If you take the masses of these two elements now and convert them into moles, you'll now know how many moles of carbon and hydrogen are in our original hydrocarbon. So using carbon's molar mass, we get 0.154 moles of carbon. And then using hydrogen's molar mass, we get 0.3085 moles of hydrogen. If we divide the number of moles of carbon and hydrogen by whichever is smaller, and that's the 0.154, we're going to get a simple mole ratio. This turns out to be 1 mole of carbon to 2 moles of hydrogen. And whatever the mole ratio is in the balanced equation, or not the balanced equation, whatever the mole ratio is in the compound, that's the same as the atom ratio. So therefore, this compound must have an empirical formula of CH2. Now, if we know its true molar mass, which they said was 85 plus or minus 5 grams per mole, we can go one more step and actually predict the molecular formula. I'll need to take my empirical formula CH2 and calculate its molar mass. So the molar mass of CH2, it has 1 mole of carbon in it, so 1 multiplied by 12.01, and it has 2 moles of hydrogen, so 2 multiplied by 1.01. That gives me 14.03 grams per mole for the molar mass of our empirical formula. The real compound has a molar mass somewhere between 80 and 90, so I'm just going to pick the number right in the middle, 85, and I'm going to divide 85 by 14.03 and see how many times it goes into it. It's going to go into it close to an integer, and this goes into it about 6 times. That means the only way for the real compound to have a molar mass of 85 grams per mole is if we have something 6 times bigger than the empirical formula. So if you multiply the empirical formula by 6, you will get the molecular formula for the compound, which is C6H12. Problem number 2, a compound containing only carbon, hydrogen, and nitrogen is combusted, and if 9.96 grams of the compound are combusted, it yields 16.01 grams of carbon dioxide and 4.37 grams of water. If the molar mass of the compound is 160 plus or minus 10 grams per mole, determine its empirical and molecular formulas. So in problem number 2, just like number 1, we have raw data for the combustion of an unknown compound, although this compound contains 3 elements now, carbon, hydrogen, and nitrogen. Oxygen will combine with carbon to form CO2. It'll combine with hydrogen to form H2O, and there's going to have to be a third product in this reaction, but they just didn't give us any numerical data about it. But nonetheless, from our carbon dioxide and water data, we can actually figure out the empirical formula. The carbon dioxide data, just like in the last problem, is going to be able to tell us how much carbon is in our original unknown compound. Because carbon dioxide is 12/44 carbon, if I multiply it by that ratio, I'll figure out how much carbon is in the CO2. And because all of the carbon in the CO2 came from our unknown compound, there must be 4.369 grams of carbon in our original unknown compound sample. The 4.37 grams of water will allow us to calculate the mass of hydrogen in the water, because water is 2/18 hydrogen by mass. If I multiply by that ratio, I will calculate that this water sample must have contained 0.4897 grams of hydrogen. And because all the hydrogen in the water came from the unknown compound, 0.4897 grams of hydrogen must have been in our original unknown sample. So our original sample, we now know how much carbon was in it and how much hydrogen was in it. We just don't know how much nitrogen is in it. So that can be done by subtraction, because we measured the mass of the compound before it was combusted. It was 9.96 grams. And we've now just calculated 4.369 grams of it is carbon and 0.4897 grams of it are hydrogen. That cancels out carbon and cancels out hydrogen. The remainder after the subtraction is just going to be the mass of the nitrogen. So we've therefore determined that this original sample must have contained 5.101 grams of nitrogen. I now know the masses of all three elements that make up the unknown compound. So from the mass data, we can determine the empirical formula. We'll take the masses of all three elements and we'll convert them into moles. Using carbon's molar mass, this sample must be 0.36378 moles of carbon. Using hydrogen's molar mass, this sample must be 0.4849 moles of hydrogen. And then using nitrogen's molar mass, this sample must contain 0.3641 moles of nitrogen. If I take the number of moles of all three elements and divide them by the smallest number, which is the 0.36378, I'll get a simple ratio of moles between the three, and this comes out 1 mole of carbon to 1.33 moles of hydrogen to almost exactly 1 mole of nitrogen. The 1.333 moles of hydrogen is not within 1/10 of an integer, so this is not a 1-to-1-to-1 ratio. If I recognize 1.333 as actually in fractional form 1 1/3, that means I'm going to have to multiply all three of these number of moles by 3 to get them into integers. So if I multiply them all by 3, I would have 3 moles of carbon. I'd have 3.999 moles of hydrogen, which is almost exactly 4, and I'd have 3 moles of nitrogen. Empirical formula must be C3H4N3. Like in the previous problem, if we know the empirical formula and they've given us the molar mass of the true compound, which is about 160 grams per mole, I can calculate its molecular formula by first determining the molar mass of our empirical formula. So the empirical formula contains 3 moles of carbon, 4 moles of hydrogen, 3 moles of nitrogen. Add those up, that comes out to be 82.10 grams per mole. If that's the molar mass of the empirical formula, and the real compound has a molar mass of somewhere between 150 and 170, I'll just pick the number in the middle, 160. I'm going to go 160 divided by 82.10, and this is going to come out close to an integer. And in this case, the integer we get is 2. Means the real molecule has to be twice as big as the empirical formula. So if you double the empirical formula, you will get the molecular formula of the compound, which is C6H8N6. Question number 3. Elemental analysis of an unknown pure substance indicates that the percent composition by mass is 94.70% carbon and 5.30% hydrogen. A solution that is prepared by dissolving 6.76 grams of the substance in 50.00 grams of chloroform has a boiling point of 63.35 degrees Celsius. Parentheses, the normal boiling point of chloroform is 61.20 degrees Celsius, and its molar boiling point constant is 3.63 Celsius degrees kilogram per mole. Part A, determine the empirical formula of the substance. In question number 3, we were given actually percent data about the compound. It's 94.7% carbon and 5.3% hydrogen by mass. So in this case, I'm not given raw data. I'm going to take my percentage data and I'm going to assume I have a 100-gram sample of the compound. If I do, it would therefore be 94.70 grams of carbon and 5.30 grams of hydrogen. When you have the masses of all the elements that make up the compound, use their molar masses to convert them into moles. So this sample must contain 7.8851 moles of carbon, and using hydrogen's molar mass, it must contain 5.248 moles of hydrogen. Divide each of those by the smallest number, and that's going to give you a simple ratio, and that ratio comes out 1.50 moles of carbon to 1.00 moles of hydrogen. The 1.50 is not close to an integer. It's almost exactly 1.5, so I'm going to multiply both of these number of moles by 2, and I'm going to get my empirical formula of C3H2. Part B says calculate the molar mass of the substance. It doesn't mean add up the mass of 3 moles of carbon and 2 moles of hydrogen. That's the molar mass of the empirical formula. That's not the molar mass of the actual substance. We're going to do this from the colligative property data given in the problem, because they've told us that we've dissolved the substance in chloroform, and they've figured the boiling point of the solution. And so if chloroform naturally boils at 61.20 degrees Celsius, and the solution's boiling at 63.35 degrees Celsius, we can subtract those and get the change in the boiling point. And if we know the change in the boiling point, we can then calculate the number of moles of solute that must have been dissolved. I'm going to do that by taking my colligative property equation and rewriting molality as moles of solute per kilogram of solvent, and then solving this expression for moles of solute. So the moles of solute will equal the kilograms of solvent multiplied by the change in the boiling point, divided by the molar boiling point constant, and divided by the value for I. So the solvent was the chloroform. They said 50.00 grams of chloroform, so that's going to be 0.05000 kilograms. The change in the boiling point is 2.15 Celsius degrees. The molar boiling point constant was given in the problem, 3.63 Celsius degrees kilograms of solvent per mole of solute. And the I value for this would have to be 1 because this unknown compound is being dissolved in chloroform, and it's not going to actually break apart into ions. It's not an acid. It's not an ionic compound. So we would assume an I value of 1. If you multiply this out, you're going to wind up getting the number of moles of your unknown that must have dissolved in the chloroform, and that comes out 0.02961 moles. The molar mass comes from taking the mass of the unknown that was dissolved in the solution and dividing it by the moles. And they said we had 6.76 grams of the substance dissolved into the chloroform. So 6.76 grams of our unknown hydrocarbon type compound divided by 0.02961 moles, and we get a molar mass of 228 grams per mole. Part C, determine the molecular formula of the substance. In Part A, we determined its empirical formula. In Part B, we determined its molar mass, so we'll now use both of those bits of information to determine the molecular formula. First thing we have to do is determine the molar mass of our empirical formula, which was C3H2. So this empirical formula contains 3 moles of carbon, it contains 2 moles of hydrogen, and if we add that up, the mass of 1 mole of the empirical formula would be 38.05 grams. The molar mass of the compound we just determined, this compound, was 228 grams per mole. So if I take the 228 grams per mole and divide it by the empirical formula's molar mass of 38.05 grams per mole, I'm going to be close to an integer when I make this division. This comes out about 6. That means the real molecule must be 6 times bigger than the empirical formula. So you multiply C3H2 by 6, and we get the molecular formula of C18H12.